So similarity relationships are really important because they can be used to solve problems involving similar shapes. And you'd be surprised how many situations where you have a diagram and you don't see two similar triangles or something. But if you start connecting points and lines and creating shapes, you can actually see that similar shapes, especially similar triangles, are formed all over the place. And if they are similar, that means there are proportional relationships, and you can write what's called a proportion, which makes it really easy to solve a problem involving the characteristics of those shapes, like finding a missing distance between points, like the height of an object or the distance from one spot to another. And so we're going to walk through that in this video. And so you want to watch this video and take some notes and refer back to this if you're having trouble solving some of the problems in the latter part of this assignment. So first of all, these two shapes are similar. And so if we have two similar shapes, we know a couple things about them. They have equal corresponding angles and proportional corresponding sides. So let's talk about what those two things mean. So equal corresponding angles just means when we talk about corresponding sides, those are the same parts of congruent or similar shapes. So we use the word corresponding. So what that really means is, for example, is that like the hypotenuse of the small triangle and the hypotenuse of the large triangle, we would say those are corresponding sides. The right angle on one triangle and the right angle in the other triangle, we would say those are corresponding angles. They sort of play the same role and they're in the same position in the shape. The shortest leg of the small triangle and the shortest leg of its similar triangle, we would say those are corresponding sides. They just play the same relative role in that shape, kind of like the youngest child in one family and the youngest child in another family. They kind of take up the same position in that situation. Okay, so that's what corresponding pieces means. So we have equal corresponding angles between these two triangles, and we have proportional corresponding sides. So what that means is the ratios of each pair of corresponding sides is going to be the same. So proportional just means that two ratios are the same. So ratios formed by corresponding sides are equal. And again, that's basically what proportional means, is equal ratios. So let me show you what I mean. So with this shape, I'm just going to give each shape some side lengths, and we'll choose a scale factor. So let's say this is our 3, 4, 5 right triangle, and let's say this has been dilated with a scale factor of 2. So that means, remember from the previous investigation, that our new sides would be 6, 8, and 10. And so what it means for proportional or corresponding sides to be proportional means that if we choose two corresponding sides, let's say we take the hypotenuse. So AC on the large one. So AC, the ratio of AC on the large one to AC, that's the corresponding side on the small one. Notice that's equal to 10 over 5, which can be simplified to 2 over 1. There's our scale factor. And that situation is true for all pairs of corresponding sides. So we could also take, let's say, AB on the big one divided by AB on the small one, so a ratio of corresponding sides, and we would get 8 over 4, which also equals 2 over 1. So that's what it means for similar polygons to have proportional corresponding sides. Is if you compare a side and its copy for any pair of corresponding sides, you're always going to get the same ratio. So Without writing it out, you can see if we took the shortest side, so BC and BC. So BC on the big triangle is 6, BC on the small one is 3. 6 divided by 3, you get 2 again. So that scale factor shows up in each of those. And one more thing to notice is that we were looking at this as a dilation of the small triangle to make the larger triangle with a scale factor of 2. And notice my drawings aren't exactly to scale. I didn't carefully make this have a scale factor of 2. I just kind of eyeballed it. But anyways, if we look at it in one direction, we have a scale factor of 2. All the side lengths are doubled. All of those ratios of corresponding sides give us a ratio of 2. We could go the other way also. If we had said, well, let's say our original triangle was the big one and we were comparing it to the small one, notice our scale factor would be times 1/2. And so if we took all of our ratios and flipped them over, it would still be true that all of the corresponding sides form proportions. It's just that this time, instead of it being 10/5, it would be 5/10, which would be a ratio of 1/2. 4/8 also has a ratio of 1/2. That's one of those equivalent fractions. And 3/6 also has that ratio of 1/2. So let's practice this a little bit with this problem. So what is the scale factor relating corresponding sides between the two similar triangles below? So we are saying that these are similar, which means they must be related by a scale factor. This little squiggle sign, it's like not an equal sign, but that little squiggle, the tilde, is the mathematical symbol for similarity. So what is the scale factor relating corresponding sides between the two similar triangles below? And so you want to show your work and then check your thinking. So try solving this, figuring out what the scale factor is first, and then use this video to check your work instead of just watching this video. So remember, in the problem up above, in the example up above, I should say, you could find the scale factor by choosing two corresponding sides and writing them as a fraction, and then simplify that if possible. So on this one, I made messier numbers. So what we could do is, so for example, we know that if we take this ratio, let's say AC, let's use the hypotenuse, and compare that to AC on the smaller one, that should give us our scale factor. And it doesn't matter which pair of sides you choose as long as they're corresponding sides. So I'm using the two hypotenuses, the longest side of these two. And so that would be 6.5 over 4.3. So it's okay to get out your calculator here and see what that simplifies to, because this is not a good way to write a scale factor because it's not a very useful number to use if you were making predictions. So if we simplify that, we get 1.5. And notice if we did the same thing for any other pair of sides, you would get the same answer. So if we did, let's say, AB, a large one, over AB on the original small one, we would have 3.6 over 2.4, which again gives us 1.5. So there's our scale factor, SF for short, right there. And you could also do it with the other one. 5.4 divided by 3.6 also gives us 1.5. Also, like the previous notes I talked about, you could also look at this the other way. Maybe if the original triangle was the large one and the dilated triangle was the small one, and you flip these all over, you get the scale factor going the other direction. So we found that this scale factor would be 1.5. We could also look at it this way. And so if we take those ratios and flip them over, so let's say we took the two hypotenuses, we did 4.3 over 6.5. Instead, you would get 0.6. And so as fractions, a little extension, connection to those fractions, 1.5 as a fraction is 3/2. And 0.6 as a fraction, that one's actually rounded off like 0.67, would be 2/3.